Welcome everyone to the CLUS Community Climate Forum. This is our first climate forum. And for those of you who are not familiar with the Center for Land Use and Sustainability, we are an applied research center. We're housed in the Geography or Science Department, but we're an interdisciplinary center. And the research that we do supports sustainable decisions in our community. So we have a lot of community partners that we work with, and we do research to help them make better decisions. We engage students in all of our work, including organizing the climate series. So Ben Stein down here at the front is a CLUS student fellow and has also, he's a political science major and also an SGA. And he has been helping us on a number of projects, including helping to organize the climate forum. So, by the way, I should introduce myself. My name is Claire Jantz. I'm a professor in the Geography or Science Department, and I'm also the director for the Center for Land Use and Sustainability. So we decided to launch a series of climate talks that we wanted to be open to the public and to the campus community. You probably know we're also streaming this live, and we're going to be recording it so it's available later. But the reason we wanted to do that is, as you all probably know, that climate change, global warming, all of these things have been coming up in the media really frequently over the past year or so, I think, especially. And it seems like there's always a new science report or an agency report or a climate protest or an international meeting that comes up related to climate change. We also know that a lot of folks have questions about climate change. You know, how does the greenhouse gas effect, how do greenhouse gases affect our climate? How does the greenhouse effect work? What changes have we seen in our local area? What can we expect to see in our local area? How can we mitigate? How can we adapt to climate change? And so for our first speaker, we're going to be focusing kind of on the basics of climate change. Later this year in November, we're going to have the president of the Ruffed Grouse Society join us to talk about impacts on wildlife. And we thought that was, you know, since November is when we see opening of hunting season, we thought that would be a good time to learn about impacts on forestry and wildlife. So, so today we're going to focus on the basics, and I'm really pleased to introduce Dr. Tim Hawkins as our speaker tonight. Dr. Hawkins holds a PhD in geography from Arizona State University. He regularly teaches Intro to Atmosphere, Sustainability, Meteorology, and Climatology. And recent research, he's been looking at the impacts of climate change on the water cycle in the Delaware River Basin. So whenever I have a question about climate or weather, Dr. Hawkins is the guy I go to. So we're really pleased to have him here with us tonight. Just a note to the folks who are streaming live, if you're joining us online, you can use the chat window to communicate with us. Ben is going to be monitoring the chat window, so if you have any issues with audio, please let us know. The way we're going to run this is that Tim will come up and talk for maybe 45 minutes or so, and then we'll open it up for questions. And if you're online and you have a question, please feel free to share it in the chat window, and then we'll capture it and communicate it to the room. And when we get into the Q&A, I'm going to ask Dr. Hawkins to repeat the question to make sure that it gets captured in the live feed. So without further delay, let's get into it.
All right, well, thank you, Dr. Jantz, for that introduction, and thanks everyone for coming. Appreciate you coming out tonight. We'll talk about sort of current knowledge, anticipated impacts, and practical solutions associated with global warming, and we'll sort of treat this as a global warming 101 type of speech here. So we'll start at the beginning, or at least the basics. You've probably all seen some sort of graphic similar to this. Global temperatures from 1850, this is the instrumental record to the present. You'll notice, obviously, towards the end of the record, starting about 1980, have been the warmer years on record. 2018 was the 4th warmest year ever recorded. You'll notice that 2 and 3 and 4 years prior to that, we had a spike in the temperatures. Can I point with this? Yeah, there we go. All right, so we had a spike in the temperatures right here, and you'll see spikes along the way. So warming isn't necessarily consistent. It's not sort of this linear ramp upwards. Those spikes generally correspond to El Nino years, and so you can see that it was projected that these were going to be historically warm years because of the rising trend that you see, in addition to the fact that we had an El Nino occurring at the same time. So there are other things besides global warming that affect global climate, but the upward overall trend is certainly one of those factors. We're in a geography department. It's always good to look at maps. So here is a map. This is actually an animated map of temperature departures over time, starting in 1880. You can see down the bottom there, 1880 to 1884. It's an average. I'm going to step this through time. So I will push play and get this rolling here. And what you'll notice as this is animating through time is that warming or cooling are not consistent geographically. Some years are warm, some years are cold. Some places are warm, some places are cold. You just saw a little bit of a warming bubble there. But starting in about 1980, which is right about now, watch how you get a pretty significant color change. All right, and so we hit that point around, late 70s, early 80s, where we have anomalies every year that are warmer than what we've had in the historic temperature record. You'll notice a couple interesting features on here. This again is sort of 2014 to 2018, but it's sort of a good indicator of how things have changed over the last century or so, in the sense that land masses have generally warmed more than oceans. Oceans have a higher heat capacity, so it takes more energy to change their temperature. The northern hemisphere has changed and warmed more than the southern hemisphere, because there's more land primarily in the northern hemisphere. And Arctic regions generally have warmed more, and there's this whole feedback mechanism between melting snow and a warming planet. You'll also notice, interestingly, a blue dot, where'd my cursor go? There it is, a blue dot right about there, and you're looking at a lot of the meltwater coming off of Greenland, causing the ocean temperatures there to be relatively cold, which causes the air temperatures in that area to be relatively cold. If you've ever seen The Day After Tomorrow, they spend about 13 seconds in that movie describing that little blue dot. So I wouldn't watch the movie other than, maybe find that interesting. You can find the science in there. It's not a great movie. We do have a little zoomed in map here, so we can look at the global perspective. We can also look at the United States. And in the United States, we have variability in how much we've warmed. The Northeast has generally warmed a fair amount. The upper Midwest has warmed a fair amount. The Southwestern United States has warmed a fair amount. Alaska has warmed a fair amount, and probably the most of any state in the United States. But the Southeast has actually cooled to some extent. And that has to do with the proximity to the Gulf of Mexico. And you've got sort of this moderating effect of the ocean and the high humidity in the atmosphere that would cause that to happen. Locally, we can look at Franklin County temperatures, and actually we mirror pretty nicely what's gone on globally, in the sense that our century-long trend has been on the order of 1.8 degrees. So the warming we've experienced locally is pretty comparable to what the globe has seen on average. So why is this all happening? Sort of a basic greenhouse effect discussion here, just relatively quickly. I like to think of global warming as the greenhouse effect on steroids. The greenhouse effect is natural. It's the reason you are here. We would not be living on this planet. Life would not exist without the greenhouse effect. But essentially, the same way your car heats up on a sunny day, our atmosphere reflects a bit of sunlight. The atmosphere absorbs a bit of sunlight. And most importantly, it lets a fair amount, about half of the solar radiation, penetrates through the atmosphere and is absorbed by the surface of the Earth and causes the planet to warm up. That's a good thing. Otherwise, it'd be too cold to live. Because we have a temperature, we emit heat and give off that radiation. A fair amount of that, most of that, in fact, is actually absorbed by the atmosphere and then re-radiated back down to the surface of the Earth. And it's that loop that we know as the greenhouse effect, okay? What global warming is essentially pumping up the carbon dioxide and other greenhouse gases in the atmosphere, which, like the glass in your car, have no effect. If you made the glass in your car thicker, it would have no effect on the sunlight. The sunlight would still come through. What would change, though, is the amount of heat that's able to escape, right? And so we're trapping more of that heat, still allowing basically the same amount of sunlight through, okay? So that's the general idea behind this. At this point, I think it makes sense to sort of back up a little bit and think about, you know, how do we know this? How long have we known this? If we want to go back further than this, we could go back to the Greeks. We could go back to the Romans, who were talking about changing the constituency in the atmosphere and what effect that would have. But in the modern scientific time period, we can go back to 1859, when John Tyndall was predicting that changes in the gas concentration in the atmosphere could change climate. As early as 1896, we were making actual calculations of global warming from human CO2 emissions. We started to model it prior to 1900. So all these things you hear about nowadays, we've been doing this for like 120 years now. In 1938, we acknowledged that global warming was already, in fact, underway. In 57, we were noting how important the oceans were in taking up carbon dioxide and what effect that would have. In the 1960s, I'll show you the Keeling curve in just a minute, but in the 1960s, we started to actively measure carbon dioxide because we knew it was important. Through the 60s to the 1980s, there were literally thousands of studies published on global warming, what the causes, what the effects were. And back in 1988, famously, Jim Hansen testified before Congress. He was sweating, and so were all the senators, because it was about 98 degrees in Washington, D.C. that day, and predicted that the warming has begun. And he actually predicted what temperatures would look like in the year 2020, and he was pretty close to right back in 1988. The first international report on this came out in 1990. So I say all of this to make the point that, you know, if you listen to sort of mainstream media, cable news outlets, wherever you get your information from, you might think that like this has all come up in the last 20 years and people have sort of agendas, they're trying to do this or they're trying to do that. But the reality is, from a science standpoint, we've been talking about this stuff for a long time. And the basic science about the relationship between greenhouse gases and what its effect is on atmospheric temperatures is, I don't want to sort of bring it down too low, but it's kind of like chemistry 101. It's physics 101. This is not real complicated stuff. What we should do about it, what global policies we should do to deal with it, those are very interesting questions. But whether or not it's happening or not, we had this figured out for a really long time. Another interesting point that sort of goes along with that. So this is a study on the consensus of consensus studies, right? So there have been seven studies that have looked at scientific consensus. They've interviewed scientists, they've interviewed the public, they've looked at scientific literature, and across the board, all 7 of them show that well over 90% in most cases of the scientific literature out there supports the notion that the planet is in fact warming and humans are mostly the cause of that, okay? The top graph is showing along the x-axis here, expertise in climate science. So these are the folks on the right-hand side that have studied this stuff, have degrees in this stuff, have been researching this for years and decades. And on the other end of the spectrum would be the people who don't, right? Generally the lay public, you know, I know a lot about climate. I don't know a lot about, you know, American literature, right? So this would be, you know, it's not necessarily that these are bad or, you know, unintelligent people. They're just not climate scientists. And so if you look at the scientific consensus then on the y-axis here, what you see is that the people that know what they're talking about, it's on the order of 97, 98% agree with the statement that the planet is warming and humans are mostly the cause. And it's the talking heads on cable news that might say otherwise, down here around the 50%. You know, sort of that, well, maybe it's happening, maybe it's not, okay? Again, from a science standpoint, this issue is put to bed. There's lots of issues that aren't, that are related to this, but whether the planet is warming and whether the humans are mostly the cause, that one's a pretty well agreed upon notion here. So what are we actually talking about? Well, here's greenhouse gas concentrations. These are measured at Mauna Loa in Hawaii. This is the Keeling curve, named after Charles Keeling, who I mentioned on the previous slide, who had the idea back in 1957 that, hey, this could be a problem. Maybe we should actually start measuring it. So we have, and you can see clearly carbon dioxide concentrations have been increasing steadily through time. We recently passed 400 parts per million. It's not much. Take a million molecules and only 400 of them are carbon dioxide, but it matters. Those 400 parts matter. Pre-industrialization, before we started burning fossil fuels, down around 275 parts per million is where we were. There's nothing magical about 400 other than it's sort of this line in the sand that we just crossed, and now people are talking about 420, 450, 500 parts per million in terms of where we may be going in future decades. Notice there's also a cyclical pattern to it. And so we are here, this graph is actually from the end of September. And so you can see we are at the sort of the low peak in this, the end of summertime in the northern hemisphere where most of the vegetation, this is the greenest the northern hemisphere will be. As we start to head in towards winter, the leaves start to fall, photosynthesis starts to stop. Those carbon dioxide concentrations will start to go back up and then they'll start to drop again come next spring. So this is the modern instrumental record. We can go back a whole lot longer than this. These are ice core data back 800,000 years. And you're looking at the top carbon dioxide concentrations along the top. You're looking at methane concentrations along the bottom. Methane is a very powerful greenhouse gas in the sense that it traps a lot of heat. And then in the middle, you are looking at how the temperature has changed over the last 800,000 years. Again, these data come from ice cores pulled out of Antarctica. And what you'll notice is that the greenhouse gas concentrations and the temperatures are pretty much in lockstep. So as one goes up, the other goes up. And as they go down, they both go down together. You'll also notice that there's clearly a cyclical pattern to them. And those are the ice ages that you're probably all familiar with, okay? So we are currently in a non-ice age, warm temperatures, relatively high greenhouse gas concentrations. And the point I want to make with this is climate varies, no doubt about it. You could fit, though, however, an average line through this blue carbon dioxide curve that would sort of represent what mean conditions have been over the last 800,000 years. And here's where we are today to scale, way off of that chart. Same thing with methane. It's more dramatic, though. You could fit an average line somewhere through here. Here's where we are today, again, to scale. So to say that climate varies and this is just a warm phase we're in, sure, climate varies. This is not a normal warm phase that we're in. These greenhouse gas concentrations are way out of the realm of normal from anything we've seen in the last 800,000 years. So what does it mean as we move forward? So you're looking here at projections of future climate. There's a lot to digest on here, but let's sort of work through it here quickly. This is historically what we've done, okay? In the black, the gray shading is the range. As we get closer to the present, we're more confident, and so we have sort of a little less confidence as we move further back in history. And then we can move out into the future, looking at future projections to the year 2100, and then some of these climate models that are making these projections continue all the way out to the year 2300. The colors in the future projections are what are referred to as RCPs, representative concentration pathways, which are essentially emission scenarios. What we don't know about the future is what are people going to do. On the red course, we're going to continue, sometimes referred to as business as usual. We are going to burn fossil fuels the way we have been burning them, and the result of that is our fossil fuel emissions are going to increase, and that's what you can see on the red line here down on the bottom. The blue curve are the temperatures that will result is if we make, as a human society globally, a dramatic reduction in our greenhouse gas emissions, what you're seeing in the blue curve down here in the lower right. That assumes a massive conversion over to alternative energy, solar, electric cars, basically electrifying our entire fossil fuel society so far. And that gets you a different result. Okay, note that in all cases we do warm. It's just a question to the degree of warming. And so you'll note here that, you know, by the year 2100, we're projected to increase from maybe a degree to a degree and a half to on the order of 5 or 6 degrees. If we keep on this business as usual, we'll be off the charts, literally off the charts on this particular graph. And to put that into context, you might say, well, who cares? All right, a couple degrees doesn't matter. The temperature varies, you know, 30 degrees over the course of a day. All right, who cares? Well, to put it into context, the last ice age was only 5 degrees Celsius colder than we are today. So 1 degree matters a lot. 5 degrees matters an enormous amount. This planet will be completely different 5 degrees warmer in the same way it was completely different 5 degrees colder than the last ice age. So that's sort of the motivation here. It's a geography department. Let's show some more maps. So As you've sort of probably starting to recognize, there's not a consistent geographical pattern associated with this. And so you're looking at low emissions along the top, high emissions along the bottom, moderate emissions in between, mid-century, end of the century, end of the next century, and the spatial pattern of warming. Again, note, land generally warms more than oceans, north generally warms more than south, poles generally warm more than equatorial and temperate regions. And the interesting thing is this point in this moment in history, we can basically choose which one of those maps we want to live on. We're probably not getting any colder than this or less warming than this, but this would be doable. There'll be some adaptation necessary. There'll be some disruption, but it's probably doable. This is not doable. That is a completely different planet from where we stand. So there's a huge range of what this could look like in the coming decades to centuries. The other side of the climate coin is precipitation. And you'll notice that you don't have the same impact, or you don't see the same clear trend that you do in temperature. And there's some good reasons for that. It's a little bit wetter nowadays than it was maybe earlier on in the historical record, but you don't have sort of that upward ramp like we had with temperature. There are, however, spatial patterns. So these are model predictions of what precipitation will look like in 2080 to 2099 relative to historic values in 1985 to 2005. Low emissions, high emissions. The high emissions show sort of a more pronounced pattern. And what you'll note is that areas that are generally wet right now, like the equatorial region where we live, most of Europe, into the poles, those areas are projected to get wetter. If you have a lot of moisture and you warm the atmosphere up, you will evaporate more moisture and you can hold more moisture and you can have bigger clouds and make more rain. If you live in a desert, like in parts of Africa or in the southwestern United States, if you warm the climate up and it's already dry, it's going to get drier. And so this is very much in line. So the fact that we have sort of not really a real obvious trend globally, spatially, there are some very distinct things that are going on. In the United States, you can see that same pattern where the eastern United States is generally expected or generally has gotten wetter and is projected to continue to get wetter, and places like the desert Southwest have gotten drier and are really projected to dry out. So you take a place like Phoenix or Los Angeles or Las Vegas and the booming populations out there and take away the water supply, you're going to have issues. I'll be real curious to see what happens in the next 10, 15, 20, 30, 50 years as this evolves. The other part of the precipitation side of the coin is we're expecting things to get more intense. So longer droughts, more intense rain. And so what you're looking at here is the percentage of land area. So it's been increasing over time, the land area in the United States, where the total annual amount of precipitation. So if you get 50 inches of rain per year, how much of that came from one event? And increasing, you're seeing like, yeah, we got 50 inches of rain, but 20 of it came on one day. And if you get 20 inches of rain, they had 50 inches of rain in Houston 2 years ago with some of these tropical storms that start stalling. When that happens, it's catastrophic in terms of the flooding that people get. So we're seeing more and more intense events as you're supercharging the atmosphere and it's able to hold more water vapor. So you can see that here in this graphic. Locally, again, we kind of mirror what's going on globally in the sense that there's been a slight uptick in precipitation over time, but it's not the way it was with temperature. But what I think you can really see in this graph best is notice that the green line here is pretty tight in terms of its variability, with the exception of maybe 1930, the drought then. But otherwise, it's when you start getting to about 1980, the thing starts going all over the place. That's the increase in variability that we're talking about. When it rains, it pours, and when it doesn't, you're in a drought. All right, we're starting to see more of that. Neither of those are necessarily good things. Let's pivot a little bit and think about, as you warm the planet, what's the most obvious thing that we're going to see? And that's going to be a change in what we refer to as the cryosphere. That is the frozen part of the planet. So you're looking at historic snow cover in black, and then projected snow cover in for a bunch of different scenarios. And not surprisingly, over time, you're expected to see that decrease. Okay, that has implications as you melt the snow and the planet turns from a lighter white to a darker green or brown or blue. You're going to start absorbing more radiation, and that'll cause the planet to further warm as we progress here. When you look at continental ice sheets as another indicator, you're looking at, in this case, Greenland and Antarctica. and both are experiencing significant mass loss over the last couple of decades here. In the case of Greenland, it's pretty much everywhere geographically. In the case of Antarctica, it's confined mostly to the West Antarctic part of the continent. And in fact, much of the rest of the continent is actually growing in terms of the ice, but the losses on the western side far outweigh the gains everywhere else. What does this result in? Well, for the oceanographers out there, this is the big issue, right? So this is the one we're interested in, global sea level rise. When you melt all that ice, that water needs to go somewhere. In addition, as you warm the ocean, they're going to physically expand the way a hot air balloon would expand. So it physically gets larger. We've got good records back to the 1700s because we have such a history of, humanity has a history of sort of the nautical past. And so we have tidal records, we have sea level height records for much of the world. And so you can see how it's risen over the last century or so, and then how it's projected to rise into the future. Obviously, if you're in a coastal location, a rising sea level is critical, but I would argue that's not the big issue. So you're looking here on the left at our local region. So here's the Chesapeake Bay, here's the Delaware Bay, the Outer Banks of North Carolina, up into New York, the Hudson River area, places that most of you are familiar with, the Jersey Shore, into Philadelphia as well. And those red areas represent areas that would go underwater from a 1 meter level of sea rise, 3 feet, right? So it's not much. I would argue that's bad, but the much more problematic issue is now bring a hurricane through. Now even just bring a regular big winter storm through, and you've got 3 more feet of extra water. If you've ever been to Lower Manhattan, down by the Battery, and looked over the edge at the water, it's about 3 feet down until you hit it. So raise that 3 feet, bring a nor'easter through, and all of a sudden, Wall Street's underwater. That's the financial capital of the world. What do you do at that point? I mean, those are the issues that I think are much more important. Add 3 more feet of pressure to all the seawalls in New Orleans, bring Katrina through. That's 3 more feet of pressure on those walls, and more levees and dikes start breaking, and then what happens, right? So I think those are really the important issues. Yes, stuff will go underwater, but what about the flooding during storms when you have higher sea level? Let's think a little bit about Pennsylvania. I think it's good to always sort of focus. Sometimes we get big picture and it's hard to sort of wrap your head around it. I like these types of graphics. What we're showing here is if you imagine the climate, the projected climate in Pennsylvania from these climate models, imagine what that would be and compare it to places today that we know what the climate is. Pennsylvania in the future, under a high emission scenario where we are in eastern Pennsylvania, will feel like Georgia, right? There's nothing wrong with Georgia, but if you've been to Georgia in the summertime, it is not Pennsylvania. It is a significantly different place. Alabama or Mississippi for western Pennsylvania. Again, livable, but very different. And if we feel like Georgia, what does Georgia feel like? All right. And if Georgia feels like Brazil, what does Brazil feel like? Well, you can't go any further south, right? You hit the equator. So maybe we're starting to look at temperatures that we haven't seen on this planet in many millennia. Some other things to think about. We could whole talk being some of these other talks, but things that are important to Pennsylvania: crops and dairy, obviously. Not all bad necessarily. There's some talk of maybe getting a second crop season in, right? We might be able to double plant, but bring a hot, dry summer, and those corn plants are not going to be happy, and neither are the dairy cattle. Overall, forest health generally is not projected to be sustainable into the future. I've got a colleague, Claire and I do, that is working on a project looking at exactly this thing, and so we'll have some results on that soon. Disease-borne vectors is a big concern. West Nile virus, things like that. As you start to increase the temperature, some of these diseases that we've thought of historically as tropical may become more relevant in more temperate climates like we have here. Recreation, we're kind of marginal at best for a ski climate. Warm the temperatures up and it starts getting really dicey in terms of whether it's a good proposition. Heat waves is arguably the thing that's going to be most important. All right, so already we're seeing an increase in that. We have had tens of thousands of people in Europe and Russia and India in the last couple of years have died. You're seeing more intense heat waves. We're pretty well adapted to deal with that, but not all northern cities are. Back in 1996 in Chicago was sort of the quintessential heat wave. And you combine that with what we call the urban heat island effect, and the fact that cities are just warmer in general than the surrounding rural countryside, and sort of a perfect storm for a significant loss of life. Again, usually the elderly and the young are the ones that are most impacted. So that's a big concern, especially in places like the Middle East, where it's already sort of pushing the limits of where humans can live comfortably. And if you don't have air conditioning, you start bumping those temperatures up even further. There could be some interesting stories in the future here. Claire mentioned some work that I've done here and some colleagues, so I'll just quickly point it out. We've looked at the Delaware River Basin, one river basin over from where we are. We're in the Susquehanna, and a lot of the stuff I'm talking about here applies to the Susquehanna as well. But we're expecting stream flow to actually increase in a lot of the local rivers here, primarily because we're not going to have any snow in the winter, and that snow is going to fall as rain. And so the black line represents historic winter runoff, and the red line represents projected winter runoff. And you can see the snow cover changing here from the historic past to what it might look in the future under different global warming scenarios. And so you lose that snow, a lot more runoff. Now you're going to make management decisions. Are you going to have enough water left over for the spring and the summertime? Are you going to have too much water in the winter? Are you going to have erosion and flooding? Do you let releases out of the dams in the fall? I mean, there's all sorts of implications for this. A colleague in our department, Dr. Voltamata, some of you know him, has looked at some of the data I produced from the climate models, has looked at flooding potential on some of these smaller watersheds. And across the board, we're expecting the peak flood value to increase. So generally, we don't care about how much water's in the river. We don't really care about the graph I made. What we care about is what's the maximum amount of water at any time, because that's when it's going to cause a problem, right? And so we're looking at those across the board increasing under all different climate scenarios. So that's a concern. Let's pivot again and talk about what some of the problems actually are and what's sort of at the root of all this stuff. As you can see here, starting in 1830s, we're looking at global primary energy consumption around the planet. And for most of humanity and human history, it was wood, right? That's what we mean by biomass. And so we were burning wood. And then with the advent of the industrial age, you start to see coal, oil, and natural gas coming online. And by the present, that's essentially all of our fuel. All right, there's still a little bit of biomass going on, mostly in the developing world. There's a little bit of alternative energy and nuclear. But overwhelmingly, we're still talking about fossil fuels in terms of where we get our energy from. Well, who's using most of this stuff, and what are therefore the CO2 emissions from it? When you burn coal, when you burn oil, when you burn natural gas, what results is carbon dioxide. Heat, light, energy, all that results too. So don't get me wrong. I mean, there's a reason we're doing it. It's good stuff, but perhaps there's another way we can get those same benefits without producing the greenhouse gases that we're talking about here. So China is the biggest polluter. You can see them here. And notice it wasn't until recently that they really started to ramp up as their economy has exploded in the last couple decades. Their greenhouse gas emissions have gone hand in hand with that. The US was in first for a while. We are now in second place behind China. But collectively, China and the US have a greater total contribution to global emissions than the entire rest of the world, excluding Europe, down here in the blue, and India in the purple, okay? And the line on this graph that's the most concerning is the purple India line. That's the one that's the concern. China has developed, and they're at the point now where they're starting to say, hey, they're investing massively in solar, massively in alternative energy. They know they have a pollution problem. They want to deal with that because their air quality is terrible. India is at the point where they're saying we are in abject poverty, and the best way to deal with that is to get people electricity. If we can do that, that'll solve a lot of problems. The cheapest way to do that is to burn coal. So that's the big concern. You take the billion plus people, nearly 2 billion people that live in India, and have them all start living like Americans, we're going to be in big trouble. We can do whatever we want in this country, and it's not going to make a difference. You can see that here when we look at a per capita rate, we don't look so good. All right, so here's the United States. By far and away, when you divide the total contribution of greenhouse gases by the number of people, we pollute way more per person than anybody else, including China, right? China has way more people than we are, so their per capita emissions are nowhere near where we are. Here's an interesting graph. So the black line is the same black line you just saw. That is the global emissions over time, and they are going up, okay? You'll notice that they drop when we have big international global events, like the global financial crisis back in 2008, right, the oil crisis back in the 70s, the savings and loans in the 80s, and also big geopolitical events like the dissolution of the Soviet Union. Because when that happens, when these things happen, economies tank, and production goes down, and so carbon emissions go down as well. So emissions are rising with a couple blips along the way. That's generally not a good thing. The other line here is that our emission intensity is actually dropping pretty dramatically. And so what emission intensity is the amount of carbon dioxide to generate $1 worth of economic goods in this case. There's lots of ways to measure it. This is in US dollars. So what we're saying is for every dollar we produce, we're doing it more energy efficiently. That's a good thing. Seems odd that we're being more efficient, but our emissions continue to arise. Why is that? Well, because there's almost 8 billion people on this planet and we're not slowing down. And those people in India are trying to live like Americans. And so their individual consumption is going up. So we need to deal with that issue. We need to somehow electrify India, pull India out of poverty, but not use fossil fuels to do it. That's a big step. Is it doable? I think so, but it's not easy, certainly. This is one of my favorite graphics. So what you're looking at here is the 10 most populated countries on the planet, the width of each of these countries. So the United States is here on the left. You got China and India. The width is how many people live there. So China and India are the widest because they have the most people there. The United States is not all that big, relatively speaking, to those two countries. The height of each of those bars is how much per capita emissions are associated with each of those countries. All right. So again, the U.S. does not look great on this. We put out a whole lot more pollution per person. And the problem is what happens when India and China are as high as the United States, right? That is an enormous amount of people. It's an enormous amount of carbon that would be put into the atmosphere. And so that's really the crux of the issue here in terms of dealing with this problem. The nice thing is we actually know exactly how to solve this problem. This is not a difficult problem. I take that back. This is not a difficult problem to understand. It's a very difficult problem to solve, but it's not like we say, wow, this stinks and we have no idea what to do. We can say, this stinks. We know exactly what to do. It's just a question of, are we going to do it, all right? So what you've got on the right here is those same emission scenarios. So we got sort of a worst case of pollution there with our emissions, best case in the blue. And what that translates to, if we take the red line and say, all right, well, we're good. We'll stay on the red line. If we stay on the red line, we come over here, we will warm on the order of 4.5 to 5 degrees. Okay? If we're okay with that as a society, then fine. If we choose that path, we know exactly how much carbon we're allowed to put into the atmosphere over the next couple of years, next couple of decades, that will allow us to hit that target. Most people agree that's a terrible target. Most people would say we need to get on the blue path, or at least one of these moderate paths. And if we get on the blue path, that'll keep our warming below 2 degrees Celsius. That's sort of the generally agreed upon value that we're shooting for. We want to hit 2 degrees Celsius or stay below that. We can probably deal with most of the worst side effects from 2 degrees of warming. In order to do that, we know exactly how much carbon we can put into the atmosphere as a function of that. Okay? The question then becomes, how do you slice the pie? Who gets to put that carbon into the atmosphere? Is it the US because we have an economy that won't work if we don't get that carbon allowance? Is it China because they're continuing to grow? Is it India because they haven't really grown yet? Is it the rest of the entire developing world? That is the difficult question. But the math behind this is not particularly difficult. Okay? Again, if you study this stuff on a regular basis. How might we get there? So how might we actually reduce those emissions? So there's lots and lots of people have ideas about how to do this. Here's one graph that I think sort of helps show what we're talking about. So these are the 15 biggest economies in the world. Okay, so you got the usual players: the U.S., China, India, a lot of Europe, Canada, Japan, Australia. The U.S. is this blue wedge right here. And so essentially, in order to get our carbon emissions to where they need to be to keep the warming below 2 degrees Celsius, we need to start 9 years ago in 2010. But you know, there's room for catching up. But we needed to have started already and reducing our emissions such that by 2050, they're about 80% of what we, or excuse me, they're about 20%. We reduced by about 80% from where we are currently. Okay, is that doable technologically? Absolutely. Politically? I don't know. We'll see. China is allowed to continue to grow. They're the bottom wedge, so they get to continue to get bigger. And then about 2030, they need to start to ramp it down. India is allowed to grow the entire time, but not crazily. The idea would be that however the US figures out to reduce their emissions, we can then transfer that technology to other economies, and hopefully they can use that technology to keep some of their emissions down. So this is one possibility in order to get us there. How do we get there? Vote. You can recycle all you want. You can become a vegetarian. You can get rid of your Hummer and buy a Prius, or better yet, get rid of your Prius and get a bike. It doesn't matter. And I don't say that to sort of dissuade you from doing all that stuff, but in the scheme of things, what matters is policy at the national level and even at the international level. So if this matters to you, vote. Guess who the one person on this slide is that doesn't have an explicit climate change policy? I won't mention it. It's not a political statement. It's just a statement of fact. For the first time ever, the Democrats held a climate town hall, and they literally talked for 7 hours on CNN. It was ridiculous, but they talked for 7 hours about climate change. So people are starting to get it in a way that they haven't gotten it before. You're seeing all these student protests. All three of these Republican candidates have explicitly said climate change is happening. Humans are most of the cause. We need to do something about it, including Joe Walsh, who is a Tea Party Republican from Illinois. All right. So if anybody was not going to say this, just stereotypically, it would be him. This guy in the bottom left, my cursor's not working. There it is. This guy down here, he's saying it. Okay. So vote. It matters. Why does it matter? Because we need to do stuff like this. Not necessarily this, but this is sort of one example. One way people talk about reducing emissions is through what we call a cap and trade. And essentially, governments would set a cap and say, we cannot pollute more than this. Every individual business cannot pollute more than this. And over time, that cap comes down. And if you go over the cap, you have to pay for that right to do that. And people that underpollute can sell their right to other people to pollute. And so there's a whole market that starts to develop. Pennsylvania actually just joined a regional greenhouse gas initiative with the rest of the northeastern United States that's trying to do exactly this. The problem is it's a little bit complicated, right? You have to set up markets, you have to set up a mechanism to do all this. A much simpler way would be a tax. But I just said the T word, and that T word is just nuclear dynamite. You cannot touch it if you're a politician. But conservative economists, progressive economists all agree that a tax makes sense. The only people that don't like it are the current Republican administration, because they run on a tax, don't raise taxes platform. And so we need to sort of get over that phobia, because if you think about the economic costs of this, this is just sort of one example, right? So we could charge a $300 tax on every ton of carbon dioxide. That would be sort of the extreme end, but that would go a long way to solving this problem, okay? Just to put some numbers on it. What that would actually mean is you would pay $2.60 more at the gas pump for every gallon of gasoline. And can you imagine if we did this? People would go insane, and rightfully so. But what if at the same time you reduce the income tax to balance it out, right? I'm not saying we just ramp up the price and everybody gets hosed, but we could somehow ramp up the price on this, get the benefits of reducing the carbon emissions, and then add a benefit somewhere else that would account for this. What that actually means is you could do this and not pay any more at the gas pump simply by trading in a Ford Explorer for a Ford wagon, right? So is this going to happen? No, I don't think it's going to. I don't think it's a prayer of happening politically. But my point in saying all of this is that, is it really that bad if you drive a wagon versus an Explorer? I mean, it's not like I'm telling you to lose your lights or to get rid of your flushing toilet. I mean, it's not that big of a deal. Yes, we have a lifestyle we're used to, but it's not that big of a deal. So it's a relatively minor cost, right? And we could probably figure out better ways to do it, but it just puts some numbers on this. The cost of not doing anything, I think, could be potentially catastrophic, especially in the developing world. Here in the United States, we're going to be a lot more resilient to some of this stuff because we got the infrastructure, we've got the money to deal with it. Go to Bangladesh, one of the poorest countries in the world. The entire country is literally a floodplain. Raise the sea level 3 feet, bring a Category 4 hurricane through, and now you've got millions pushing 1 billion environmental refugees. And where are they going to go? To India, where they already have a couple billion, pushing 2 billion people? All right, that's the problem here. How are you going to deal with that? Africa, we've seen a lot of famine in the relatively recent history. the whole continent is projected, or much of the continent and some of the Saharan areas are expected to get drier in sub-Sahara areas. You think about the Middle East, it's constantly in the news, geopolitics there. A lot of the places you hear about, like the West Bank, that is the west bank of the Jordan River, which is the water supply for a lot of the places we're talking about when we talk about the Arabs and the Israeli conflict, right? You think that problem's going to get better if we dry up the water supply? A little bit more local to home, I mentioned this already, but bring a big storm through New York City and now you put Wall Street underwater, right? What happens when the global financial crisis or the global financial center goes underwater? What people are talking about nowadays is what's referred to as the Green New Deal. This is sort of this moonshot. This is sort of the most recent sort of revitalization of how people are thinking about this. And it's this expansive program, probably too expansive to realistically get done, but what politicians are trying to do is get people on record as being in favor or not in favor of it. And then voters will decide, right? Realistically, none of this is going to happen. But again, to put some numbers on this, it would cost about $10 trillion to electrify this economy, the United States, okay? That means your cars, your heating, your air conditioning, a lot of that stuff is electrified, but anything you use fossil fuels for right now would be turned into electricity from solar panels, from wind, and from nuclear is probably a realistic part of the mix there, okay? So it's a lot of money. $10 trillion is a lot of money, but it's a one-time cost that will then lower and make predictable our energy costs for the next half a century. We will no longer be reliant on Middle East oil and global sort of swings in the geopolitics. The infrastructure that we will build will now last for 20 to 50 years, during which time we'll probably make improvements and have replacement stuff when it dies. And the job creation and being a leader in the world economic market would be similar to World War II. We spent an enormous amount of money ramping up for World War II. We then reaped the benefits all through the 1960s and the 1970s of that economic development, and that's what basically made America the superpower that it has become. To put it into context, we spend $1.25 trillion on Social Security and unemployment, $10 trillion the U.S. construction industry plays. We pay $3 trillion in healthcare, both private and public. So $10 trillion as a one-time cost compared to comparable values that we spend on an annual basis, it's a lot of money. But it's not like ridiculous money, right? And it wouldn't all be at once. And the jobs and the benefits, it would probably end up being a net benefit overall. And if you can avoid the worst costs, it seems like a reasonable expense to pay. How are we doing so far? Well, not so great, right? So these are those same projections. You see that we are clearly in this big circle here, projection for 2018 on sort of the worst case scenario. Doesn't mean we can't change paths in the future, but it's going to take some sort of lifting, okay? So to not be all doom and gloom, I think we can talk about some ways around this. The reason we're out of balance is our emissions here versus, there we go, our emissions here, our deforestation is contributing carbon dioxide. We are absorbing carbon in the atmosphere. We are absorbing it in forests. Trees take up carbon, and we're absorbing it in the oceans. We are out of balance by 5%. We put 5% more in than we take out. Therefore, we're going to keep on warming. It's just a matter of math, okay? We could plant more trees. The easiest thing would be to put less carbon into the atmosphere and not cut down forests at the same rate. Can't really fix the top one. Can't do much about the bottom, but we could reforest areas and really let marshes come back. That would be a huge help. So that's why we're out of balance overall. And again, to not be total gloom and doom about this, I actually am relatively positive. Unfortunately, I think it takes a sort of catastrophic event in order for some of this stuff to happen, but it has happened in the past. We did something. So in the United States, we passed the Clean Air Act and the Clean Water Act back in the 1960s when we said, okay, enough's enough. We're happy to have a growing economy. We're happy to have all our stuff. We're happy to make a lot of money, but people dying because they're breathing the air and rivers literally catching on fire is not acceptable. Okay, so let's stop that. Let's maybe ratchet it down a little bit and have a better environment to live in. By the way, that was a Republican that set up the Environmental Protection Agency. That was under the Nixon administration. So it's not like Republicans haven't thought this way in the past. It's just sort of where we are at this current moment. The Montreal Protocol was an international agreement, so that could be a potential template that removed chlorofluorocarbons, which are one of the main ingredients in propellant cans and coolants, refrigerators, and they destroy the ozone layer. We basically banned them internationally. It's worked fairly well, and the ozone hole is in fact recovered. recovering. It's a bit of a simpler problem to tackle compared to global warming, but it is a template for how we might do this. I would argue that the United States needs to lead on this, because when we lead, stuff happens. Like when we thought the Russians were spying on us with Sputnik, we created NASA and put a man on the moon 10 years later. We have resources, we have money, we have the ability to potentially do some of this stuff. Regardless of your opinion about how World War II ended, the fact is when we entered World War II, the United States, it ended, right? We defeated the Germans, we defeated the Japanese. The world is different, right? So it's not these sort of superpowers slugging it back and forth here. China has risen into a global power, so things have changed, but I would still say we still have some of the same issues, right? So you've probably heard of the Paris Climate Agreement. There are 200 countries that agreed in 2015 to shoot to keep warming well below, whatever that means, 2 degrees Celsius, and to limit emissions. They were going to make pledges as to how they were going to do this, okay? The reason this happened was because President Obama and Xi Jinping of China got in a room together for 3 days straight and did not leave until the start of this meeting and basically came up with an agreement. They came up with an agreement. The entire rest of the world got on board, okay? It's not perfect. It's nowhere close to perfect, but it's a start. And again, it's that leadership, in this case, probably China and the United States, and maybe India. And what they did is they pledged to reduce their emissions, right? So the US pledged to reduce this much. The rest of the developed world pledged to do this. This is what China said. This is what the rest of the world did. And so overall, you see those emission pledges. If we don't do that, we would stay on the red line and warm 8 degrees Fahrenheit. If the pledges hold the way they have, we'll be at 6 degrees Fahrenheit. That's too much. We want to be at 3 degrees Fahrenheit. But again, you update these every 5 years. So we start, you make a pledge, see what works, see what doesn't work, update it again. So you notice here, right, we updated, here's our 5-year pledge, right? And then we flatline. There's no reason we couldn't make a new pledge in 2020, which is when the next one is due. And that is when we could potentially reduce something at that point. Guess what else happens in 2020, right? So Donald Trump, one of the things he said when he came into office was, I'm out of this Paris Agreement. It's stupid. I don't like international agreements, okay? Well, he didn't actually, because he can't. He can't leave until 2020, and he can't leave until, like, I don't know the exact date, but it's like November 12th, 2020. It's days after the next election. So what can you do? I am not telling you how to vote. If you want to vote for Donald Trump, that's fine. But from a climate standpoint, that actually matters. More than anything else, this 2020 election matters from a climate standpoint, because this is what's going to determine what the U.S. does, and what the U.S. does will probably determine to a large extent what the United States will do after that, okay? So that's what I got. I'll leave it there. That was like a whirlwind tour, and there's 1,000 hours worth of stuff we could talk about, but I haven't taken any questions if anybody has any. Yeah, Logan.
We're talking about the blue, like the best case scenario at this point, where we keep warming around 2 degrees.
Yep.
Would there be any chance that we're like recovering even more than that over time, or are we kind of just stuck there?
Yeah, so that's a good question. So the question was, the blue line showed 2 degrees maximum of warming. Is there any chance of doing better than that or recovering from that? The short answer is no. And the reason is because carbon dioxide has a life cycle where it's going to stay in the atmosphere. So we put it in there now, the temperature will respond and it's going to stay there. And more importantly, the oceans will warm, and it takes a long time for those oceans to change temperature. So whatever emissions we put out there, we're stuck with that amount of warming for hundreds and in some cases thousands of years, depending on where you go to. So the goal is to cap it and flatline it and not keep it ramping up. Now, people talk about geoengineering, and you could, in theory, suck some of that carbon dioxide out of the atmosphere. How to do that at a scale that is meaningful and doesn't cause 15 other problems, we don't have a lot of confidence in that. But we may get to the point where this is bad enough that the technological solution, rather than just like stop burning fossil fuels, we decide to invent something to remove the pollution. We could get to that point at some point. That would help reduce things. But realistically, we're probably looking at picking the cap and where we're going to flatline for the next couple generations. Yeah. Yes, sir.
I appreciate your presentation, but it's the easy part of the problem. You've got all this statistical data that's science-based, and physical laws and all that. Going to bring in the history department and the psych department and talk about changing human nature, because that's where it's going to be.
Yeah.
You've got to have that.
Yeah, I agree.
And the reason this country is the way it is because in the last 40 years, I'd say since the Reagan administration, people in this country have chosen the SUVs. They've chosen the skygraph on polluted fuels. We made that choice. It's not just Trump, it's the entire American public. How do you correct that?
Yeah. So the question was, just for the folks online, was I gave the easy part of the presentation, which is the science and the math, because it doesn't lie. It's the people that are the problem, and we've made a choice as a society over time to burn fossil fuels, to drive bigger cars, to have more energy-intensive buildings. I agree 100%. And the problem with global warming is it's as a species, we are wired to like run away from the saber-toothed tiger, right? If you're about to get eaten, you will do something. If your family can't put food on the table, you will do something about that. Whether your grandkids have a habitable planet or your great-great-grandkids have a habitable planet, yeah, we care. We say we care. Everybody, I think, would say they care, but are you going to actually do something about it? As a society, the answer absolutely is no. And yeah, I mean, the psychology of that is fascinating. And so, it's this sort of now versus later, and that's the problem with this. The other interesting thing is sort of a related topic is this. What you're seeing here is very similar to what played out with cigarettes. A couple decades ago, where at some point, you smoked cigarettes because it was good for you. It made you skinny, made you feel good, right? It got you through the day. And now, people might still smoke, but nobody's going to say it's good for you, right? I mean, so that. It took like 30 or 40 years to get to that point. I think we're getting there with climate change. We're still in that like maybe year 10, year 20. But I think we're going to look back a couple decades from now and be like, really? Like, were we really that dumb about all of this? Whether or not we do anything about it, I don't know. The problem with climate change, cigarettes, go ahead and smoke, it'll kill you. At some point people stop smoking and they won't die. That's not true with climate change, right? If we don't deal with it now, future generations are going to suffer for that. So I don't know is the short answer to your question. And that's one of the real interesting things to think about is how, and people have researched that. I mean, there's been lots of social science on that, but it's a tough nut to crack. Absolutely. Yeah.
In that graphic that you showed with the 9 maps, and it was like low emissions and high emissions, what does life, in like your opinion, what do you think it looks like on that worst case?
Yeah, so on that worst case scenario. So that's, again, 200 years in the future. If we just keep on burning through all the fossil fuels we got, we are down in the bottom right-hand corner. And you're looking at warming on the order of 11 degrees Celsius. That is 18 degrees Fahrenheit. That's twice as much in the opposite direction as the last ice age. I don't know. I mean, it radically different, unlivable for many people, I would say, in the sense that you probably can't live around the equator. You probably literally can't live around the equator unless you have air conditioning, because at some point you hit a temperature which allows for a dew point to get so high that you physically can't cool yourself. We're getting close to that in some Middle Eastern places now and in places in India. So that's a concern. Again, the big problem with all this is how fast it's happening and the species adaptation. The short answer is I don't know. I don't think anybody really does. But I'm pretty confident that there won't be 8 billion people on this planet. I don't know how many there will be. I don't think we'll go extinct, at least not in this time frame. Realistically, I don't think climate change would ever cause us to go extinct because the haves will always find a way to technologically advance and, protect some people, I think. We might get more clustered. You might get, I don't know. I mean, who knows? World War III could break. I mean, it will not be good. I guarantee you it will not be good if you hit the bottom right corner of this. Yeah.
Going off of what you said, there won't be 8 billion people left. So let's say we get to that point and half the population of Oregon is cut in half, and people still go on with burning fossil fuels. Will that slowly over time, like if there's a dramatic decrease of people burning fossil fuels, will that slowly go back to the top left?
Yeah, so the question, again, I think I forgot to mention the question for the last one, but the question was if we have a rapid reduction in population or a huge reduction in population, what will happen to CO2 emissions, assuming nothing changes in terms of how people behave? Yeah, so the short answer would be, again, you're locked into some amount of emissions. And once you get to this point, there's so much energy in the oceans that you're probably, it's not, you may reduce the emissions, but you're not necessarily going to cool the temperatures from that standpoint. Yeah, I don't know. I mean, it's something that, you know, it's even for me who cares about this stuff, it's hard to actually like picture what 200 years in the future would look like under that scenario. I mean, it's going to be some dystopic sort of sci-fi novel. Yeah, Sean.
So, you know, looking at it from the, you know, the sort of geology perspective and looking at the rock and mineral resources perspective, we talk about the production of fossil fuels. I mean, basically, we're already on the downward trend of our available traditional oil, and now we're looking at sort of those marginal, or what we call non-traditional fossil fuels. Obviously, you know, the natural gas, you know, appetite that we've been ramping up, that will sustain us for maybe 3 to 4 more decades. But when we get out to 2070, 2080, we really don't have much left, especially with the population that we've got. So at what point, right, do we decide we have to wean ourselves off of that fossil fuel, because we're going to get to that, you know, that end moment where we crash, where we don't have those resources and we've not done enough to protect our climate for the alternative. So, I mean, have you thought a little bit, and I haven't read that part of the IPCC.
Yeah.
Do they look at, you know, the total end point of the mineral resource production?
Yeah, so the question was, you know, at some point we're just going to run out of fossil fuels. The problem is that point is further in the future than the time frame we need to be acting from a climate standpoint. So again, it gets back to the issue of, you know, well, I'm making money off of this. I'm living in a nice house. Climate doesn't seem so bad to me. You know, who cares what happens in 2070 when this oil runs out? By then, we'll have another technology that will work with us. So I think that's part of the problem from an attitude standpoint. I think it really is more of a social science question. The problem is, you know, eventually, yeah, we're just going to run out of this stuff. But in the meantime, how much damage are we causing along the line? So, yeah, I mean, I'm not too familiar with the peak oil in terms of the social side of it and what people are thinking about. But the timeline is such that it just doesn't work from a climate standpoint, and that's the big problem with this whole issue. Yeah.
I'm just curious what your thoughts are on how to effectively replace fossil fuels and sustainable fuel sources with sustainable ones, since, like, if I remember correctly, things like gasoline, petroleum, natural gas, and such have a much higher level of potential energy than things like solar power and hydroelectric. So how do you efficiently replace those energy sources while still helping to maintain the standard of life that they're not going to go better?
Yeah, no, that's a fantastic. So the question was, how do we replace fossil fuels with something that's as energy intensive that will actually allow us to maintain our current standard of living? Money would be my first answer. Is research and development. We have solar panels that work, but they could potentially work better. There are physical limits to how good a solar panel can work, but they could work better. But the short answer to that is I think nuclear, at least in the short term, has to be on the table. Nuclear can pack that kind of punch. Should we go nuclear? I don't know, but I don't think you just throw it out as a concern because of terrorism or other issues. I do think ultimately solar is going to be sort of the ultimate technology that does it, but you're right. The reason we use fossil fuels is because they have a huge amount of energy per amount burned. But I think if you could, there have been several studies that look at the geographic area necessary to cover the planet in terms of solar panels, and it's something on the order of like 8% of the land area. I mean, it's a lot, but 8% of the land area covered with crummy current solar technology could power the entire planet. The amount of solar energy that comes from the sun in one day can easily power this entire planet, everything we do for a whole year. So we have an enormous amount of energy. We're just not great yet at converting it into electrons and electricity, storing it as batteries for nighttime, and then moving it from, you know, the Sahara Desert to northern Russia. So I think research and development is probably a big part of that, but I wouldn't throw nuclear out yet either. That's a really good question. That's the type of question we need to figure out. I mean, those are the questions we need to be asking and answering, because those are the ones that are challenging.
So I'm here obviously with the oceanography class, and one of the articles that we'll read in a few weeks is about sort of the blue carbon, or the blue carbon wave, as they talk about it. And there's already some of those, when you talk about some of the cap and trade, there are some folks out there looking for funders to be able to go out and start doing iron fertilization in the ocean. And they've run a few tests with that. Basically, the idea is to give the intermediate and mid-ocean waters a little bit of fertilizer so that they undergo bloom. And in that way, they begin to draw down carbon dioxide, both out of ocean waters, but also out of the atmosphere. Have you heard a little bit about the potential for blue carbon and what might that look like?
Yeah, so that's a good point. I don't know a whole lot about. The question was about blue carbon and the idea of like fertilizing oceans so that you get a plant bloom, which would then start to absorb carbon dioxide in the same way that land-based plants would be. I don't know a whole lot about that. You may actually know more about it than I do, but my concern with all of those types of things, if you fertilize the ocean, what else is going to happen, right? There's a reason we don't have giant blooms in the ocean right now. It's because the ocean doesn't want giant blooms. We haven't evolved that way. So what happens when we make a giant bloom, a bloom large enough to actually absorb meaningful carbon dioxide, either out of the ocean or out of the atmosphere? What else is that going to cause? I mean, that's my concern with all these geotechnology. Yeah, we could shoot all sorts of missiles up into space every day and have them explode sulfate particles into the atmosphere and reflect radiation the way a volcanic explosion would, but what happens when that stuff falls out? So I don't know, and I have no idea what the answer to that question is, but my general answer is I think it's a lot better to fix the problem than to build these gigantic, expensive, overly complicated band-aids, which is essentially what that is. Right? It's a band-aid to fix a problem when we could just stop polluting. That would be an easier way of going about this. Yeah, I don't know. Interesting though. We may get to that point where those are the best options, as some of these sort of crazy ideas to geoengineer the planet, and cross our fingers and hope it works. Well, thanks everybody. I appreciate it. I don't know if you have any concluding. Thanks for coming out, and have a good rest of the night.
Yeah, feel free to join us in November for our second seminar, and based on some of the audience conversation, I think we have some good ideas looking for topics in the spring as well. Thank you.